Hi everyone, welcome back to Dave's Math channel. I'm your host David Tare. This is my continuing feature on the Math Lovers book, and I'm on section 5.5, which is on functions. And like I said yesterday, I'm going to do a total 5 lessons on functions. I did one yesterday. This is my second. And yesterday I defined what functions are, their special type of relation. But now I'm going to talk about 3 different types of functions, namely injections, surjections, and bijections. I'm going to define all 3 of those and give several examples of functions that are some of these things or maybe not. Anyway, let's begin. First we have to define these things: injections, surjections, and bijections. Those names might sound a little scary. There's other names for them. Injections are sometimes called one-to-one functions. And what an injection is, we say that f of x is an injection if, for every value of y in the domain of f, there's a unique value of x such that f of x equals y. In other words, there's no 2 values of x that give you the same value of y. And if you graphed an injective function, you would find that there's no horizontal line. Every horizontal line would intersect at most 1 point on your graph. This is if it's a function of numbers. Remember, I was talking about a function. It's not even a function if the vertical lines have more than one intersection point, but it could still be a function if the horizontal lines have more than one intersection point, but it's not an injection unless there's only surjection, another name for a surjection is an onto function. And all that means is that for every value of y in the domain of f, there is a value of x such that f of x equals y. So the whole domain gets used, if you like. There's no points, there's no values of y that are not accounted for by this function. And then if it's both an injection and a surjection, this is a very special type of function called a bijection. And bijection just means exactly that. It's injection and a surjection. Another way to say it is both one-to-one and onto. And the nice thing about bijections is that they're invertible. Every bijection has a unique inverse. And I'm going to talk about inverses tomorrow. But that's why bijections are important. So anyway, now I'm just going to do some examples. So for the first example, this is a pretty easy one. Let's say f1 is a function from the real numbers to itself. So the domain and range are both a set of real numbers. And we're just letting f1 of x equals x. This is sometimes called the identity function. It really doesn't do anything. It's a function that leaves every value of x, every input alone. So the output's equal to the input. Not a very interesting, fun function from a point of view of computation. But what is this thing? Is it an injection? Yeah, it is, because for every value y is just x. So there is a unique value of x for every value of y, namely x. And for every, did I say that right? Yeah, yeah. And then is it onto? Well, yeah, because the range is obviously all of R, because y is equal to x. The domain was R, and since every element of x gets mapped to itself, every element of R gets mapped to itself. You see the ranges are as well. So it's both one-to-one and onto. It's both an injection and a surjection, and therefore it's also a bijection. You really don't have to do any extra work to check if a function is a bijection. It's a bijection if and only if it's both an injection and a surjection. So usually it just has enough to check that it's an injection or a surjection. Let's look at a second example. This one's kind of similar. But again, f2, the domain and the range are both the real set of real numbers R. And now our function is f2 of x equals 2x. So this is a little bit more interesting function. It's a function that doubles every value of the argument. So for instance, f2 of 5 is 10, f2 of 1 is 2, f2 of pi is 2 pi. You get the idea. and this actually does compute something non-trivial, although you can usually do it in your head. But anyway, so again, let's ask ourselves whether this is an injection, surjection, or bijection. And we can kind of cut to the chase with this example, actually. Can we find an inverse for this function? If it has a unique inverse, then it's necessarily a bijection. So remember, y is f2 of x, y equals 2x. Can we solve for x in terms of y? That's an easy way to determine whether a function is a bijection, by the way. If you can solve, if you can use the equation of the function y equals f of x to find a unique inverse, x equals f inverse of y, and unique. So in this case, it's pretty easy to find that inverse because y is 2x. Just divide both sides by 2, and you get x equals y over 2. So you have a unique formula for x in terms of y. So if you like f inverse of y, it's just y over 2. So yeah, it's a bijection, and therefore, since it's a bijection, it's also necessarily an inverse injection and a surjection. So that was a pretty easy example, actually. So now for the third example, let's say, so now we have the function, again, function for the real numbers to itself, but now our function is squaring. So f3 of x equals x squared. Well, let's go through the whole thing again. Is this an injection? No, it's not, because there are, in this case, there's not a unique value of y such that, I mean, for a given value of y, there's not a unique value of x such that f of x is y. There's not a unique square root. Remember, there's a positive square root and a negative square root. So, for instance, if y is 4, x could be either 2 or minus 2. And that's true for every positive value of y. The only value of y with a unique value of x is 0. F of 0 is 0. And, and so it's not an injection. Is it a surjection? Well, no, it's not a surjection either, because not every value of the real numbers gets mapped by this function. In particular, the negative numbers don't. There's no value of x such that f of x is equal to minus 1. That would be the imaginary unit, or it's negative, but we restricted our domain to be the real number. So there's no real number whose square is negative. Therefore, the negative numbers don't get mapped. Therefore, it's not a surjection either. It's not onto its domain. And since it's not an injection or a surjection, it's also not a bijection. So this example is none of those things. Um, and then example 4. Now, what if instead we did cubing? So again, f4 is a function from r to r, the real numbers to real numbers. But now f4 of x is x cubed. Well, it turns out this one. So is this one an injection? Well, yeah, it is, because every number has a unique cube. I mean, you remember the cube of a negative number is negative, and the cube of a positive number is positive. So say for instance, y was 8. So what number is cube is 8? Well, 2, and minus 2 that doesn't work for. Another way to do this, we could cut to the chase for this example as well. Let's just ask ourselves, is a bijection. In other words, can we find an inverse of f? Well, yeah, the cube root. I mean, remember the square root wasn't really unique, because you could use either the positive or the negative of the square root to get a number whose square is equal to what you started with. But in the case of cubing, when you start with real numbers, every number does have a unique real cube root. Every real number has a unique real cube root. So for this example, this is a bijection. And since it's a bijection, it's also an injection, a surjection. And I think I should mention, I mean, it's kind of weird, because if you know, this is kind of part of a general pattern here. We started with example 3 was squaring, example 4 was cubing. If we did nth powers, it turns out, where n is an arbitrary positive integer, it turns out that if n is even, then it's none of these things. It's not an injection or a surjection, and therefore not a bijection. Because for the same reason the square isn't, because only the positive values get mapped. But if n is odd, it turns out for every odd integer n, every positive odd integer n, that does have a unique inverse, so therefore that's a bijection in that case. And it's also an injection surjection. So I just thought I'd mention. So you can see that odd powers behave very differently from even powers if you restrict the domain to the real numbers. Uh, anyway, example 5. So I've got 3 more examples. Example 5. Now our domain is just the interval from -1 to 1, the closed interval from -1 to 1. That means that x has to be a real number strictly, or just between -1 and 1, possibly on the endpoints. And our range is r, the real numbers. And now we have the function f5 of x equals square root of 1 minus x squared. So we have to ask ourselves what kind of function this is. Is it injection, surjection, or bijection? Uh, it's not an injection because remember there's 2 square roots, like I said before. You know, I mean, if you just look at the thing inside, so let's say y equals square root of 1 minus x squared. We could try to solve, and then it turns out that if x was negative, say you started with, let me just do an example here. Let's say we started with x equals 1. Well, then you would get y equals 0. Square root of 1 minus 1, which is just the square root of 0, that's 0. But also, what if x is minus 1? Well, then its square is 1. So again, the thing inside the radical is square root of 1 minus 1, or square root of 0 is 0. So there's 2 values of x that get mapped to 0, namely -1 and 1. And I think for every value of the argument except 0, there are 2 what are called pre-images. There are 2 values of y, actually. There's 2 values of x that give you the same value of y, just like there were for the case y equals x squared. So it's not an injection. Is it a surjection? Well, no, it's not a surjection either, because our range was the whole set of real numbers, and I think it's pretty easy to see that the values of y you're going to get from this function are all strictly between 0 and 1, which is definitely not all the real numbers. So it's not a surjection either, therefore it's not a bijection. Example 6 is kind of similar to this, except this time we're restricting the range to be what's called the unit interval, the closed unit interval, or in other words, all the real numbers between 0 and 1, possibly equal to 0 and 1. And then I think for this example, it is actually a surjection, because I think it's pretty easy to see that any value y that's strictly between, or no, I mean, here's the way to know it's a surjection. Remember, surjection is onto. Well, I think you can see that you're never going to have start with a value of x that such an f of x is not in this interval from 0 to 1, because square root of 1 minus x squared, if you start with a number x that's between -1 and 1, I think you can see the thing inside the square root is going to always be less than or equal to 1. It's going to be between 0 and 1. And then when you take the square root, it's still between 0 and 1. So therefore, it is a surjection. But is it an injection? Well, no, it's not an injection for the same reason as example 5 was not an injection. Because, again, you're going to have 2 values of x that give you the same value of y. You can just take the negative of any other value of x that gives you a particular value of y, just like you did for example 5. So it's not an injection, so therefore it's not a bijection either. But it is a surjection. Last example. Now we're going to have the same function, except we're also restricting the domain to p, the closed unit interval, the interval from 0 to 1, possibly equal to 0, 1. And in this case, it actually is a bijection, it turns out, because now it's an injection. Remember that the values of x are now non-negative, therefore there is going to be a unique square root. So it is 1 to 1 in this case. And it's also a surjection for the same reason as example 6 was a surjection. Every value of x you start with between 0 and 1 also gives you a value of y strictly between 0 and 1. And all of them get mapped that way. Therefore, this function's onto, and since it's both an injection and a surjection, it's also a bijection. And you might wonder what its inverse is. Remember, I said every bijection has a unique inverse. If you solve for y, what's interesting is this function is equal to its own inverse. It turns out that if y is square root of 1 minus x squared, and x and y are both, strictly between 0 and 1, then it turns out that x is equal to square root of 1 minus y squared. The way you would see that graphically, the functions that are, so the way you get an inverse of a bijection graphically, if the values of f are numbers, the domain and range are subsets of real numbers, if you like. It turns out that the inverse of a function is just the graph you would get if you reflected it. If you reflected it about the line y equals x, the main diagonal. And functions that are equal to their own inverse are functions that are symmetric about that line, about the line y equals x. They're kind of rare, but this is an example of such a function. Y equals x is another example, kind of a trivial example. Because if y equals x, then x equals y. So anyway, so that concludes my video for today on injections, surjections, and bijections. So thank you for watching. Long live math, and I'll see you guys next time. Bye.